Welcome to lecture number 43 of the Statistical Thermodynamics course. Now, in this previously, if you recall, that we wrote that in the case of vibrational transition, the vibrational partition function is written in this particular form. Now, we can now do the two standard partial derivatives that we are well accustomed with right now. One is T ln z vibrational dt constant v is equal to theta v by t exponential theta v by t minus 1. And then you have t squared in z vibrational by dt equal to theta v by t squared by t divided by exponential theta v by t minus 1 square. So on this particular basis, these are the two standard partial derivatives for the partition function. So on the basis of this, we can now calculate the vibrational contributions to internal energy, enthalpy, and heat capacity, CV. Okay, so U by RT for the vibrational contribution is H by RT vibrational is equal to theta V by T divided by E theta V by T minus 1. Then CV by R vibrational is equal to CP by vibrational is equal to theta V by T square E theta V by T divided by E theta V by T minus 1 whole square. So for the vibrational contributions to entropy, we have S by R vibrational is equal to theta V by T divided by theta V by T minus 1 minus ln 1 minus exponential theta V by T. Okay, the significance, so the significance, you can see this vibrational significance of these vibrational contributions to thermodynamic properties can be seen in which if you plot, if I generate a plot, which actually will show this in a little bit more details. So this is say theta by theta v. Okay, and this will be the vibrational contributions, okay, to whatever, it's the internal energy or specific heat. So initially the contribution, so you can mark certain things like 0.5, 1, say 2, 3, something like that. So initially for a part, there is no contribution. So then it starts to pick up a little bit. And then, of course, this goes like this. Okay, so this is like U by RT vibration. You can see the upswing, and if we mark this scale, if this is 0, so this is about say 0.2, 0.4, 0.6, right, 0.8, about 1. Okay, so it is below 1, of course. Okay, so it is like that. CV shows a little bit of a faster rise, like this, almost asymptotes. So this is like CV by R vibration. Okay, so as you can see, that the specific heat does not display classical behavior until at least we have the specific heat does not exhibit classical behavior till t by theta v is equal to 2, okay, which basically corresponds to t almost equal to 2000 to 12 Kelvin. In other words, smooth, full excitation of the vibrational mode to replicate the classical results will be in the limit t approaches infinity, u by RT vibrational is equal to 1. And then limit t approaches infinity, CV by R vibrational is equal to 1. Okay, so it requires very high temperature. Okay, so as you can see from this particular figure, that the classical limit of internal energy is delayed compared to the specific heat. This is the delay, right? Hence, in contrast to translational and rotational mode, vibrational mode is typically only partially excited near room temperature. Okay, so when equipartition principle, while the equipartition principle applies at sufficiently high temperatures, okay, so these predictions will be completely inappropriate for vibrating molecules at 300 to say 2500 Kelvin. Okay, so exceptions are of course there, but so you can understand that this is what it is. Okay, this is what it is. It is only activated closer to about 3000 Kelvin. So let's do a simple math problem now. So employing simplex model. Okay. Calculate internal energy U kilojoules per mole for AIO real 1000 Kelvin. Okay. So now we know already what the internal energy will be composed of. Okay. So it will be like U by RT is equal to U by RT translational plus U by RT electronic plus U by RT rotational plus U by RT vibrational. Okay, so the translational component, as we all know, that U by RT translational is equal to 3 by 2. Okay. The electronic contribution obviously requires that you evaluate it from the data. So there is an appendix K2, for example, K.2, where you can calculate the first two energy levels. Okay. And again, the next energy level is very high. As a result of that, you don't evaluate, you don't go up to that level. Okay. And because of our choice of zero of energy, we convert from the T formulation to the T naught formulation. So recall that T naught is equal to TE plus half omega E prime and omega E double prime. Okay, so if we now look at a table, just a sample table, so say TE given as centimeter inverse, omega E centimeter inverse once again, T naught centimeter inverse, GJ, then EJ by KT, then GJ into EJ by KT, and then of course EJ into EJ by KT into exponential EJ by KT. Okay, so this is 0. This is 979.2. T naught is 0. The degeneracy is equal to 1. EJ is equal to 0. And then GJ by this is equal to 2. And this is equal to 0 once again. Then of course the second one, 5046. So now you convert this is 728.8. T naught now will be equal to 5281. Gj on the other hand is 4. Okay, this EJ by KT is 3.799. Then Gj into this is 0.0896, and lastly this will be 0.3404. Okay, so employing this table, now we can obtain the corresponding electronic contribution. So therefore URT by EL, the next energy level is too high, so we are neglecting it essentially. It's not activated, or the probability is very low. As you can see, it kind of gets down, it kind of decreases, okay, in an abnormal way, okay, as we go higher and higher. Okay, so so let's look at it. Okay, so this is EL. Okay, so that is 0.3404 divided by 2.0896, which is equal to 0.1629. So this is what we get. The rotational contribution from the rigid rotor approximation, the rotational contribution from rigid rotor approximation, okay, is based on the rotational constant, which is BE, which is given as 0.6414 centimeter inverse. Okay, as a result of that, T by theta R, remember this is 2000 is the temperature, divided by 14387 multiplied by 0.6414, which is given as 2167. Okay, so that is the corresponding this. So we find now that U by RT rotation is equal to 1. We employ all these things. Okay, finally the vibrational contribution, we again use the harmonic oscillator model, okay, for which theta V is equal to 1.4387 centimeter Kelvin, 979.2 centimeter inverse, okay, which is 1408.8 Kelvin. So now therefore U by RT vibrational will be equal to theta V by T divided by theta V exponential of theta V minus 1, which is equal to 0.6888. Okay, now if we pack all these things together, U by RT is equal to U by RT translational plus U by RT electronic plus U by RT rotational plus U by RT vibrational. So this is given as now a summation of 1.5 plus 1 plus 0.6888 plus 0.1629. It's given as 3.3517. Okay, so the final calculation of internal energy therefore will be multiplied by RT. It will be 555,735 kilojoules per mole. Okay, so that is interesting. So this gives you a nice insight on how to calculate the whole thing. So far what we have done is that we have been calculating the thermodynamic properties of a diatomic molecule. We have assumed complete separation of the energy modes, and in reality, of course, accurate calculations will require that the simplex model is replaced by the more complex model for combined rotation and vibration. In other words, we should compare the effect of vibrational and harmonicity. So what we are missing, vibrational and harmonicity, right? Okay. Then rotational centrifugal stretching. Stretching. Then, of course, rotation vibration coupling. In other words, we need what we call a single complex model. Okay, complex model. Okay. Furthermore, the controlling mode parameters might not be associated solely with the ground electronic states, especially for molecules with low-lying upper electronic levels. Okay. So in this case, a more rigorous expression for the partition function is given as Z translation into Z internal. The internal partition function is now, the translational part is the same, is J EL J exponential minus EL J by KT, okay, to Z RV comma J. Okay, so this is the electronic part, and that is the Ro-vibrational part. Okay, so now what we see over here is that the Ro-vibronic partition function, Ro-vibronic partition function, which is given as let's write it as capital RV comma J, that inherently implies strong rotation vibration coupling, strong rotation vibration coupling. Okay, it explicitly depends on the jth electronic state via the influence of its modes potential on both the vibrational and rotational energy modes. So it depends on jth electronic level, electronic state, okay, via the Morse potential, okay, which affects both the rotational and the vibrational modes. In other words, the Ro-vibrational energy, the ERV, the Ro-vibronic energy rather, J by HC would be equal to something like, it depends on which electronic state you are in, and the electronic state is important, therefore this is J. So it's always affected by the identity of its associated electronic energy mode. As a result, this invariably requires numerical computations to properly evaluate the partition functions. There are many numerical strategies which are listed in the GenOff tables, appendix E of the book. Okay, so the idea is, now this is a rigorous model because it depends on the associated electronic state. So the thermodynamic properties would be considered to be simplified if the coupled rotational modes will be separated from the electronic energy modes. Okay, so if the rotational, the Ro-vibrational modes, if Ro-vibrational modes could be separated okay, from their electronic modes, electronic energy mode. Okay, so this gives you, this is internal, this is R Ro-vibrational, and it is summed over all J electronic, J exponential electronic J divided by KT. Okay, where now the Ro-vibrational counterpart will be given as 1 over sigma summing over V and J 2J plus 1. Okay, now let me write it. All these are within the summation still. minus hc by kT and multiplied by gv plus fvj, depends on the vibrational band. This separation could be affected. This separation can only happen if if one of the following holds. This separation can only happen, okay, if one of the following holds. Okay, so these will be like the excited electronic levels, are unpopulated. So basically you're taking out which electronic mode out of the picture. And the second one is that the vibrational rotational parameters are essentially the same. One of the two, vibrational / rotational parameters are same for all electronic modes, either one of these two. Okay, or electronic energy levels. Okay, so the most common scenario first is the presumption of sufficiently low temperature so that the entire molecular population is within the ground electronic state. Okay, so this happens typically if we choose low enough temperature. So entire population is at lowest or ground state. Okay. For some unstable molecules, okay, it's maybe a little bit different. Okay. So if we combine now all of these things together, constitute the semi-rigorous model for the partition function. The translation and electronic contributions follow those for the simplex model. Evaluation of the Ro-vibrational contribution is more complicated, and this is what we can write. Therefore, what we need to do is GV plus FVJ equal to omega E plus half minus omega XC E plus half square plus BV J plus 1 DV J square J plus 1 whole square. Okay, BV is equal to BE minus alpha E plus. Oh, okay, taking the zero of energy, if we take the zero of energy as E equal to 0, J equal to 0 within ground electronic state. Ground electronic state, we have G naught 0 plus FV 0 E by 2, so omega XC 4. Okay. Now, if we subtract this from the previous version, which is if we subtract this guy from this guy, okay, we yield the revised Ro-vibrational energy, okay, which is GV FVJ, okay, is equal to omega star, so omega star X star D into D minus 1 plus E star J into J plus 1 E J square J plus 1 whole square alpha E V J into J plus 1. Okay, so omega star equal to omega e minus 2 omega e into xc. X star is equal to omega e xc by omega star, and E star is equal to E minus half alpha E. Okay, so we can also define a characteristic temperature. Characteristic temperature for the for combined rotation and vibration. So that we can write it as RV equal to HC by K dV plus FVJ. Okay, so now if you write it in a proper form divided by T, this will be T V minus X star D into V minus 1 plus Y into, so this comes with Y, gamma J into J plus 1 minus delta V. We will write out what all the symbols are in a bit. This is what it is. And to write that T is equal to omega star omega E theta V by D, and Y is equal to V star VE theta R by T. You can understand that these all comes from the rotational, the vibrational. So gamma is equal to dE by B star. Delta is equal to alpha E by B star. Okay. So these equations that we found, okay, are basically first order corrections to the rigid rotor and the harmonic oscillator model. So these are first order corrections to rigid rotor and harmonic oscillator model. Each is a harmonic oscillator. As usual, omega E, XE, BE, alpha E, and DE are obtained from spectroscopic data. Okay. So using this, you can now calculate what will be the theta RV by T. Okay. Now, using all these things, you can now evaluate the partition function. Okay, you can evaluate the partition function, okay, which is written as, let me just finish this by writing this, RV 1 over sigma double summation EJ 2J plus 1 exponential theta on the V by T. So that is the partition function. Okay, we will, in the next class, we will see that how this partition function can be broken up into two using the Euler-Maclaurin fashion. But this is what it is. So these are all first order corrections to the rigid rotor and the harmonic oscillator model. And this is what we are going to use to calculate the remainder of the parameters. Okay, so, and we will see that how this can be employed to find out, you know, stuff like entropy and once again the internal energy and stuff like that. Okay, so this is the process, this is the procedure that one should follow when you go for a rigorous model right now.